Let's take a look at finding some more functions m of x. There's only one small difference this time, is that our beam is indeterminate. And what do we mean by that? Over here we have 3 external support forces, 2 translational, 1 rotational. At the right end we have 1, giving us a total of 4 unknowns. And we have 1 free body diagram that would have 3 linearly independent equations of equilibrium. So this beam is 1 degree indeterminate. So we need another equation. Now it's going to turn out that the equation is going to be a kinematics equation. The beam equation is going to help us solve for one of those 4 unknowns. But our use of the blue saw that we want to use to find m of x, when we have a situation where we are indeterminate, m of x, the moment on the inside of the beam, is going to be a function of one of the 4 external unknowns. So if we go ahead and take our beam now and cut it at a distance x, that's going to leave on the right hand side a segment of L minus x left. So we're just going to blue saw that thing using that free body diagram. And what's the free body diagram going to look like? It's going to have the reaction force from the roller. I'll call that F1. There's the 3 internal forces, moment, shear, and axial. And there is our external applied load, W, our uniform load. So we are going to find m of x. It's just going to be a function of a red arrow. So we're going to use statically equivalent again. So we take that distributed load W multiplied by the length, which would be L minus x. It gets put at a distance L minus x over 2. And all we do is just statics. So we're going to spin a moment right there at the cut again. And we end up with an expression for m of x. And so unlike in a determinate beam, we can't shake this red thing. We have at least one external support force, which is going to be present in the equation for m of x at this point. So we go ahead and do a little bit more math. We can multiply it out, and this is just grouping terms. There's the x squared term. There's a linear term, and there would be a constant term. So let's give you a note right here with all that. Note that m of x has a red value, and it happens to be in 2 places. That's fine, but it just has an external unknown. Now, when we integrate the second order beam equation, we're going to end up with a total of 3 unknowns. We're going to have the 2 constants of integration and F1. Is that going to be a problem? No, because we are going to have more boundary conditions. So we're going to slide right back up to the picture here. And we know in this beam we have a kinematic restraint at the right end, and at the left end, in the transverse direction, we're going to have 2. We know the deflection and we know the slope. So we're going to have a total of 3 physical boundary conditions in the transverse direction. In a determinate beam, we would only have 2. Let's take a look at a triangular load again. So all we've done is taken the example from earlier, and then there is a roller at the end. So if we count this up, we've got one external support force. Here we would have 3, so that's a total of 4 external unknowns. We've got 1 free body. That's going to give us 3 linearly independent equations. So again, we are 1 degree indeterminate. So m of x will be a function of an external support force. We won't be able to turn the roller force black. We won't be able to solve for it using statics. So there's our whole structure free body diagram. We need to take out the blue saw. and cut that thing open. And again, we always do the blue saw at X. So there it is at a distance X, giving us a free body diagram, very similar to what we saw for the determinant, except that out there at the end we've got our red F1. So we'll make quick work of this. It's got a little bit of math to follow. To go solve for m of x, we're just going to spin a moment right there at the cut. And so we got just a little bit of math to do. And there would be the expression for m of x, and there's the red thing, the external support force. All right, so, but do remember in this indeterminate beam, we actually have 3 physical boundary conditions. Let's go back up here to the original picture. Right, we would have a translational restraint at the left end. We would have a translational and a rotational restraint at the right end. So those are going to be our 3 boundary conditions for solution to movement in the transverse direction. Let's take a look at another beam similar. We've got the wall support, we've got a roller, we have an applied moment. This is indeterminate, 1 degree indeterminate. So we're going to need to use the kinematic equation to help us solve this. So we're going to take out the blue saw, we're going to cut it at a distance x. All right, note we've defined very consistently in these problems, x is defined left to right on these beams. Just helps with sign convention in bookkeeping. Cut that thing at a distance x, giving me the internal forces at x. And all I'm going to do is statics. Just go spin a moment right there at the cut. And that'll give us the expression to solve for m of x. This one's going to be a little clean, not too tough. All we have is f1 times x. And then the applied moment, m of x, just keep track of the signs. Right? There's my transformation sign convention. And so I get out of this an expression for m of x. So that's the expression I'm going to end up putting into the beam equation. We've got one more indeterminate beam to talk through here. And so a little bit different here. We've got a pin connection giving us 2 external unknowns. I've got a roller and another roller. So again, we have 4 unknowns. We have 1 structure. This beam is continuous all the way across, so that gives us 3 linearly independent equations. So this thing is 1 degree indeterminate, but different than the other beams that we've seen thus far, because we have a beam that has 2 different m of x functions. We're going to have 1 m of x that goes from the pin to the roller, and then we are going to have another m of x, which is going to go from roller to roller. That support right in the middle is going to supply a force which is going to change the internal moment. So we're going to end up with a jump in the shear diagram and a change in slope, a slope discontinuity in the moment diagram. So let's go see how we need to attack this. We're going to need 2 m of x's, so we're going to have to take 2 different cuts. So first cut, let's go ahead and let's do a look at the whole structure free body diagram. All right, there's the pin, roller, roller. And so we'll need to use the blue saw at x. As we had said, we're going to need to use it twice, once in this region and then separately over there in that region. So for x from 0 to L over 2 only, I'm going to cut this, and I am going to solve the free body diagram. I'm going to spin a moment right at the cut. I'm going to use the left-hand side there. Notice it's got a distance x, statically equivalent load from the distributed load. And so we have an expression just working through the equilibrium equations. We've got an expression for m of x. And there would be a function of the external unknown f2. I'm going to have to take a completely separate cut to be able to solve for the internal moment on the other side of the beam between f3 and f4. So I'm going to take out the blue saw back on that original free body diagram. I'm going to go ahead and cut it, and I'm going to end up using the other side of the free body diagram. So I'm going to use this side of it. And so I'm going to be able to make quick work of equilibrium. All we're going to do is spin a moment right there at the cut. And so working out the fact that we have a dimension of L minus x, so it makes it look a little more complicated. It's a little more math to kind of get through, but you end up with an expression. If you'd like to work to something where all the terms are grouped, that's what I've done. I've got the x squared term in the front. I've got an x term, and then the constant term. And that is valid only for L over 2 to L. So we have a domain that has two different m of x equations. And so we're also going to need to use the relationship eventually. And this gets a little more complex problem, but there's a relationship between F2 and F4. And that relationship is going to be established by equilibrium. And so we're going to end up with needing 5 boundary conditions to solve this problem. So the equilibrium on the whole structure free body diagram, I'm going to be able to relate F2 to F4 by taking a moment right at the middle of the beam, or right where F3 is located. So there's my other relationship right there, the F2 equals F4. Boundary condition wise, what do we know? At the left end, I have no translation, right? No transverse deformation. At L over 2, where the roller's in the middle of the beam, I have no transverse deflection. And also at the right end of the beam, I have no transverse deflection. And we're going to need to take segment 1 and segment 2, and they're going to have to link to each other, and this is called continuity. So the solution needs to be continuous across L over 2, where these two functions meet each other. And so this just says that the deflection on one side has to equal the deflection on the other side. Also, the slope has to be the same as we cross the boundary at L over 2. If the slope weren't the same, then we would end up with a kink in our beam, which would be a nonlinear beam, and this is a linear analysis. So that just says that whatever the slope is, I don't know what it is, but it has to be the same on both sides if that was going to be at x equals L over 2.